example, suppose I push a button 4, then it will generate two frequencies, signals of two frequencies. One is 770 hertz, the other one is 1209 hertz. Okay, and when this frequency is received at the exchange understands that you have dialed the number 4, and then you have all the electronic system which will be operating accordingly. Okay, so oldest systems was electromechanical. Okay, so it was based on some electromagnetic things, and dialing and all these things was based on all those things. Whereas nowadays, since it is mostly electronics, okay, and you activate different circuits in your electronic system using different frequency waves, okay, different signals of different frequencies, and this different frequency signals are decoded, and accordingly the different circuit, different parts of the circuit is activated. So this is how modern day telephone system actually works. Okay, so this is basically the dialing system. We are not going into details right now about this dialing system, because before that, what we want to discuss is, again, as I said, that I will be discussing it along with the history of communication. So basically, this push button dialing system came long afterwards, means in fact at the end of the previous century. So it was not there during that time. Okay, during that time, at the end of the 19th century, it was not there. Okay, so this push button dialing system, we will talk about it afterwards. What actually was happening that time in the 19th century, at the end of the 19th century, when Alexander Graham Bell was trying to make his telephone system better and better, okay, but he was still using wired communication, line communication. He was using this electrical lines for transmitting the voice, okay. So at that time, parallelly, some people started working, and they were trying to send this electrical power wirelessly. So they were thinking of whether it is possible that instead of using a conducting line, is it possible to send some electrical signal wirelessly? So at the end of this 19th century, this some people started working on it, and they started developing. In fact, some people were successful, and they could develop some wireless system. Okay, so this is the starting of the radio communication, the wireless communication. So the radio communication started sometime in the in the last decade of the 19th century. In 1886, actually, there's Hertz. Okay, there's Heinrich Hertz. He said that there is some radio waves that is there. Means it is there, but he was not able to generate. He said that it is there. Okay, based on physics, mathematics, and all these things, he said that it is there. Okay. And actually, Maxwell, before Hertz, actually, Maxwell gave the mathematical formulation, mathematical equation for the electromagnetic wave. And Hertz then studied on that, and he said that it is there. It is, that's what Maxwell said, it is true. Hertz basically in 1886 proposed that. Means he came up with some idea that it is that electromagnetic waves are there, and it can be produced, it can be generated like that. Okay. However, he was not able to transmit it. Okay. He just observed it. He found out that there is some electromagnetic wave is there. Okay. He could just uh, find out the existence, but he was not able to transmit that radio wave. Okay. Hertz, anyway, I think you know that the unit of frequency is named after Hertz, and it is written as Hz. That is the short form of the unit of frequency. It is Hertz, named after him. By the way, one thing I want to mention here, you can see how I have written the unit of frequency. I have written it as, when I am writing it in full form, I am writing it as small h, okay, HERTZ, small h. Whereas when I am writing it in short form, I am writing it as capital H followed by Z, okay. Now this one you just, I want to mention it here, you keep it in mind that whenever we use the name of any scientist as a unit, and when we write the unit in full form, we write it in shorthand. Means the unit will be written in shorthand. It is not capital H when I write it in full form. Okay. You might, I think, I don't know whether you have observed it, that when we write Newton as the unit of force, then we write small n, whereas actually Newton is a proper noun. Newton is the name of the scientist, and so it's a proper noun. But when we write it as unit of force, Newton, then we write it as small n. Okay, you can check it. Means if you, in any standard book, okay, if you see that all the units, when it is written in some scientist's name, and it is written in full form, then we write it in shorthand, means small cut letter. Okay. So just keep it in mind. Okay. Whenever in future you do it, don't make this mistake. Ampere, for example, the unit of current ampere, you should write A small when you write full ampere. But if you write only the initial, then you write capital A. Okay. Similarly for volt also like that. Anyway, so in 1893, after that, actually Tesla was the first person who was able to transmit this radio wave, but not a long distance. Just a short distance he was able to transmit this radio wave. So basically Tesla was the first person who said that, okay, it is possible to transmit this radio wave. So if it is possible to transmit the radio wave, then it is also possible that I can transmit some signal, and some power can be transmitted from one point to the another. So that is what Tesla, first he was able to do that. Again, here you can see that magnetic flux density, the unit is Tesla, and when we write full form Tesla, we write it small t, but the unit in, when we write it in terms of the abbreviation, then we write it as capital T. Okay. Then in 1897, Marconi was the first person who built a radio system. Okay, and in fact, he patented this radio system, and it was commercially, it was available. People were able to, some companies were able to make radio and sell it. Obviously, Marconi was able to make money out of it. Okay. And one good thing about this, all this radio communication, in fact, when Marconi was able to build this radio system, uh, one good thing is that this radio system of Marconi was used that time in the ship. All the ships started using this radio system for transmitting telegraphic message wirelessly. Because before that, obviously, the ships were not able to communicate because there was no radio system, no wireless communication. And in it actually, this wireless telecommunication, this radio system, it helped to save at least 800 lives when Titanic made the accident. Okay, because when the Titanic was sinking, that time the ship started sending lot of SOS messages wirelessly, and um, one ship, I don't remember the name, that ship was able to receive that message, that radio message, and that ship was able to reach the spot by morning, and they could find at least some 800 people still alive, and they were able to save them. So that is one good thing, that the development of this radio system, this wireless transmission, that how it helped that, yeah, at least to save some 800 lives. Okay, so 1897, Marconi built the first radio system, but we are unfortunate, we Indians are unfortunate that actually this credit should have gone to one of our scientists, Indian scientist, Jagadish Chandra Bose, because he was the person who actually made a radio system, okay, but he was not keen in going for any patent, because he was more interested in doing research and academics and all these things, and he was not interested in making money. So because of that, uh, the actual credit which he was supposed to get, this credit actually went to Marconi. In fact, many people that time didn't know for a long time that this radio system was, even before Marconi, it was built by Jagadish Chandra Bose. So this is actually the system which Jagadish Chandra Bose, he made it. Okay, this is the system he made it, and in 1895, 2 years before Marconi made his radio system, he demonstrated that it is possible to send uh, electromagnetic waves, and he sent this electromagnetic waves for a distance of 75 feet. Okay, and that also passing through two walls. There are two walls in between, and that electromagnetic wave was able to penetrate those walls. And using that electromagnetic wave, he was able to ring a bell and even explode some gunpowder. Okay, so he demonstrated it. Okay, and so 2 years before Marconi, actually he made a system. This was, so this is the one, this picture, this is still there. This is still there. If any one of you visit anytime in Kolkata, there is a Bose Institute, and there is a museum in Bose Institute where it is still there. You can see it. So this is the first ever millimeter wave communication system in the world, and that was developed 125 years ago. In 95, it was developed. Okay, so you can say that actually Jagadish Chandra Bose, he was the pioneer in making this system, this communication system. He used all these different components like spark gap transmitter, dielectric lens, coherer, horn antenna, polarizer, all these different types of things which are used nowadays in uh, telecommunication system, this wireless telecommunication system. He made all those things, although not very sophisticated at that time. It was a crude way. We made all the things in a very crude way, but it worked. It worked that time. And it was able to transmit the radio waves as long as by 75 feet. Okay. At the same time, actually, as I said, that during that time, many people were actually trying to make this wireless communication, because when Graham Bell has already made a telephonic system, then people and telegraphy system was already there. Then that time it was already the interest of many people to send the signals wirelessly, so that it is not required to send the signal only where there is a line connection. Okay, so for example, in the ship, it was possible to transmit wirelessly like that. So many people were actually trying at that time. Okay, Popov, who is another person who also was working on it, but even according to his own published paper, till 1895 end in December, he was not able to send the radio waves. Okay, he was working on it. He was not able to send the radio waves to a long distance. So that means, whereas as in the previous slide we have seen that in 1895, Jagadish Bose was already able to send the radio wave by a long distance of 75 feet. Okay. So in that way, we can say that till 1895, no one else was able to make radio communication system other than Jagadish Chandra Bose. But the problem is that he was, as I said, he was very much reluctant in going for patent and all these things. In fact, he used to say that why shall I commercialize this science? Rather than, instead of that, if whatever I am making, whatever results I am getting, that can be used by other people, that can be used by different companies for the benefit of mankind. That is what he used to say. Means he never used to say that, okay, why shall I make money out of it? But if it can be used for the good of people, then anyone can do it. Okay. So in fact, in 1897, when Marconi built his radio system and he patented it, he used this that coherer. Okay, coherer is the main device which can capture the electromagnetic wave, which can receive the electromagnetic wave. So that coherer, which was made by Jagadish Bose, that coherer was used by Marconi. The same coherer means what Jagadish Bose has made. The same technology was used by Marconi to make his radio system. Okay. So as we see that this Jagadish Bose was actually the pioneer in this field, but he was forgotten for a long time. But later on, it was found that actually he had a paper published. He had a paper published in 1895. He published a paper from Royal Society. Royal, what is that? I think he published a paper somewhere in Royal Society. Yeah, in the Proceedings of Royal Society, he published a paper in 1895, 96, 1896. That paper was published. Uh, he published his paper, and Marconi actually read that paper and he built his system. So it was found later on, and that was found out by IEEE. I don't know whether you people know what is IEEE. IEEE is, as of now, the highest body of electronic and electrical engineers. It is the Institution of Electrical and Electronic Engineers in US, and as of now, it is the highest body. And in fact, you people, I will maybe, if not now, but maybe next year or when you come to third year, by that time you will take a membership of that, student membership. Okay, because most means almost all people in the world who are working in electronic and electrical engineering, they have a membership in this IEEE. Okay, IEEE is the highest body. So IEEE actually gives the means, if you publish a research paper or a conference paper in IEEE, you are you get a good recognition. Okay, that is why IEEE is so great, that we try to publish paper in IEEE. IEEE always means is the main. You can say it is the main yeah, governing body of the engineers, electronic and electrical engineers all around the world. So this IEEE, they when they found out that there was a paper published by Sir Jagadish Chandra Bose even before Marconi, and actually Marconi used that paper to build his system. So, but Jagadish Bose didn't get that recognition. So IEEE thought of recognizing J.C. Bose, and in 14th September 2020, they declared that the work done by Jagadish Chandra Bose was the IEEE milestone in electrical and computer engineering. So they declared it, and subsequently his name already in IEEE Hall of Fame, already there were the name of Marconi and Popov was already there as the main scientist or the pioneer scientist of radio communication. So obviously they cannot take out their name any now. So what they did, they added the name of Sir J.C. Bose in that Hall of Fame. Okay. So Jagadish Bose is nowadays regarded as the father of the modern day wireless telecommunication. Okay. So that is how at least he has been honored and his work has been recognized. However, it's not that Jagadish Bose was working only on radio communication. Although he was actually trying to do things for radio communication, for transmitting radio waves, in the process, he actually also did some work on electronics also. He developed some devices, some solid state devices. Okay, and he published some paper on that. Okay, The first one, he actually developed some radio wave detecting device. Okay, as that Mercury coherer he developed, and uh, he developed a solid state radio wave detecting device during that time, 1895, 1896, which he named as electric eye or artificial eye. This is what he said. Okay, because he said that it is the device which can see the electromagnetic wave, and it can then change it to the electrical signal. So some electromagnetic wave falling on that device, it used to be transformed to the corresponding electrical signal. So it is basically a radio wave detector. Okay, that is what he did. Although he was saying it as electric eye, but this same device, Oliver Lodge, who was also trying to work on something like that, he named this as Coherer, this electric eye. He named it as Coherer. And what we can say, it was the first ever solid state diode. Before that, there was diode, but those were all vacuum tubes. Okay, so this is the first ever solid state diode made by Jagdish Bose. So in the way, actually, when he was trying to work on radio communication, when he was trying to make some radio wave detecting device, in the process, he actually was also developing some electronic devices, some solid state devices. He also made some many other wireless wave. Gradually, actually, he kept on uh, making better and better detectors and all these things. And in 1901, he made another semiconductor device, which he named as CATVISTAS. Okay. In fact, before that, there was no semiconductor. Okay. So he made it. Okay, CATVISTAS. It was a point contact semiconductor rectifier. So you can see that this was basically another, he made the diode basically. Okay, but he was not using it as a diode, but he was just using it as a detecting wave, radio waves. Marconi, in fact, used this later on. He used in his initial 1897, he used the previous coherer which Jagdish Bose made. And when Jagdish Bose made this new one in 1901, that one also Marconi used it because it was a better one. And he used it for long distance communication across the Atlantic. Okay. However, this time actually, Jagdish Bose, although he was not keen in taking patent, but this time his friend Swami Vivekananda, he pursued him that he should take patent of this work, and accordingly in 1904 he took he took patent on this. Okay, so you see that as an electronic and communication engineer, you people are means you are following the legacy of one great scientist of this country who actually has contributed in the development of both electronics as well as communication. Okay, he is pioneer in both the things. He had been the pioneer in making the semiconductor devices, and he is as well the pioneer in making the first ever wireless communication system. And in 1977, according to Neville Mott, when he got his Nobel Prize, after that, this is the remark he made that J.C. Bose was at least 60 years ahead of his time. In fact, he had anticipated the existence of P-type and N-type semiconductors. So you can see that even during that time, some 125 years before, when there was no idea of semiconductor, that time he was able to make something of the type P-type and N-type, although he didn't know much about that. So now, when I was talking about all these things, when I was talking about the history and all these things about this radio waves, now it must come in your mind, what is this radio waves? Why people were at that time so much interested in this? How these people developed it? And mostly, if you see that this radio wave was basically the physics people were actually working on it. Okay, so it is basically a physics. Okay, radio waves and all these things is physics, and we electronics engineers are nowadays making use of it. Okay, it is basically physics. Now you have I think you have already studied about this electromagnetic wave to some extent in your 11 12 class 11 12 you might have studied about it, and maybe I don't know whether in your physics course you are studying to some extent or not in here in your first year in physics you might be studying to some extent this EMO. So I'm just going to give you a brief idea. Obviously, in this course, I'm not going. I'll be not going deep into it. Okay. So as you may be knowing that when there is a means what is electromagnetic wave? Okay. Uh, so whenever there is some electric field and magnetic field, okay, when they come in contact with each other, then there is an electromagnetic wave uh, or electromagnetic radiation that is uh, produced. Okay, so you have to have electric field and you have to have some magnetic field in contact with each other. Okay, so it is basically a composition of electric and magnetic field, and they are oscillating. It will be of oscillating nature. Okay, that's why it is wave. Wave means always it should be of oscillating nature. Okay, uh, how the electric field is produced? You know that whenever a charged particle is moving, okay, uh, whenever there is a charged particle, whenever there is a charged particle, then obviously there will be an electric field around it, and that in that electric field, if you place another charged particle, so that charged particle will experience some force on it. And what will be the direction of that force? It will be the direction of force will be in the direction of the electric field. Okay, so that means if there is a charged particle, the electric field will be radially, it will be electric field will be produced radially outwards from that charge. Okay, if it is a positive charge, that field will be the field will be radially outwards. Okay, what is a magnetic field? That whenever there is a moving charged particle, whenever the charged particle is moving, that is what you have studied, that whenever current flows through a conductor, you have a magnetic field produced around it. So whenever there is a charged moving particle, then there will be a magnetic field produced. Okay. Uh, but when you place a charged particle in that magnetic field, it will experience a force, but that force will be in a direction perpendicular to the uh, that field. Okay, that will be in a perpendicular direction. Okay, so that is so this force will actually change the velocity. It will not change the magnitude of the velocity, but it will change the direction of the moving charge particle. So that is how electric field and magnetic field they are produced, and that is the physics that you have already studied earlier. So electromagnetic field is produced by an accelerating charged particle. So this is what you have. So if there is a charged particle, then accelerating charged particle, then you will be having electric field as well as the magnetic field. Okay, and hence you will be having an electromagnetic field produced. Okay. So electromagnetic waves are nothing but electric and magnetic field traveling through space. Okay, we are talking about now the free space electromagnetic waves. Okay, the wireless transmission. Okay, I will see that how. Okay, now if this oscillation, okay, the charged particle is as we are saying that it has to be an accelerating charged particle. Now, if that charged particle is having some simple harmonic motion, okay, oscillating, okay, if it is oscillating about some equilibrium position, then that oscillation is also means it is having some acceleration. Okay, and since it is an accelerating charged particle, then obviously there will be some magnetic field and electric field produced. Okay, and the what will be the frequency? The frequency will be the same of the as the charged particle is oscillating with the same frequency. The electromagnetic wave will be produced with the same frequency. The wavelength, lambda, you know that this lambda is related by this c by f. C is the velocity of light or the velocity of the electromagnetic wave. Okay, and the whole thing actually it is based on some Maxwell's equations. We'll go briefly. We'll talk about them. Okay, Maxwell's equation. Okay, so basically this is the thing. Pictorially, whatever I have said, you can see that I have some charged particle. Okay, some charged particle is accelerating along this axis. Okay, and because of that, I'll be having some electric field. Okay, I'll be having some electric field in this direction. Okay, it will be in this direction. Okay, the electric field, and that electric field, uh, I'm writing it in this way. You know that wave equation can be written in this form. Okay, so this is E naught, this is the maximum, and cos kx minus omega t, and I am using some phi, some arbitrary phase is there. Okay, uh, what is this kx? This x is this direction. This is the direction x. So basically, with time, you can see that there is some oscillation at any point. At any point x, there is an oscillation with time. So that's why omega t. Omega is 2 pi f. Okay. So you have some oscillation. Okay. So a particle, charged particle, will be oscillating at any point x at this point along this direction. Okay, it is oscillating. It is oscillating vertically, and this oscillation at different points, they differ. They differ in phase. Okay, along x, and that's why this kx is coming. Okay, this kx comes into picture because when a point, when the charged particle here is at the top, the charged particle here is at some phase difference. The charged particle in other points are at some phase difference. Okay, so like that, at different points in the x, the different particles will be oscillating with the same frequency, but they will be having some phase difference among them. Okay, so that's why this kx is. So this is this pink one. You can see this pink one is actually showing the graphical plot of the waveform of that is the electric field waveform that is formed due to the oscillation of the charged particle. Okay. Now, whenever the particle is, as I said, whenever the particle is oscillating along this direction, a magnetic field will be produced, but the magnetic field will be in the direction perpendicular to the direction of the movement of the charge. So the magnetic field is this green one, which is in a perpendicular direction. And the magnetic field oscillation, the field is given also in the same way as B naught cos kx minus omega t plus phi. Okay. And the wave, when I am having this electric field and the magnetic field perpendicular to each other, then the wave energy propagates in this direction of x. Okay, it propagates in the direction of x. So these electromagnetic waves are basically not transverse in nature. Okay, sound wave is not transverse in nature. Longitudinal waves. The sound wave is not electromagnetic wave. Okay, so whereas this radio waves, even your power line electricity, that is also electromagnetic waves. So all of these are electromagnetic waves which are of long transverse in nature. Okay. Now coming to the some of these mathematical equations, how these mathematical things are, we are getting it. Just in brief, okay. This is what you know in physics, that the general wave equation is given by y. X y is just this is a general one. It has nothing to do with this is a general one. I say that y is a function of x and t, and this is given as say there's a cosine wave a cos omega t minus kx. As I said, omega t is the with time how the particle is oscillating, and kx gives you the phase difference at different points x. Okay, so this is the x direction and this is the displacement of y along this axis. Okay, a cos omega t minus kx can also be written in this form. Okay, this can be also written like this. Okay. Now you see that what I want to mean is that this for x, okay, if x is at a distance of lambda from the beginning, lambda is the wavelength. So at this point, the phase difference will be 2 pi. Okay. Again with another lambda, the phase difference will again come out to be 2 pi. So what is this k? So this k should be actually 2 pi by lambda. So this is k factor 2 pi by lambda. So you can see that from here to here I have the phase difference given as 2 pi by lambda into x. So at this point when x equal to lambda, again it becomes the phase difference it becomes 2 pi. Okay. So like that. So I can write k as 2 pi by lambda. And omega is what? Omega is 2 pi f and f is c by lambda. So again this omega can be written as 2 pi c by lambda. And hence I can write this as this. Okay? I can write it like this. Okay? You can just simply work it out. This is how you can write it. And the differential equation, it can in fact now, if you differentiate this y with respect to x 2 times, okay, and if you differentiate y with respect to t 2 times, then you can equate them and you will see that this equation comes. This is the equation. This is the relation that you will get. Okay, this is the relation. So this relation actually relates how y is varying with x and how y is varying with t. Okay, this differential equation relates that. Okay, and so this is the differential equation for the wave motion. So this is what you might have studied in physics. So this is a general wave equation. Based on this, now we will try to relate the EM wave equation. As I mentioned some time back, that this electromagnetic wave, the physics of electromagnetic wave and all these things is basically based on 4 Maxwell's equations. There are 4 Maxwell's equations. These 4 Maxwell's equations are very important and you have to remember it throughout your career. Okay, you have to remember it. Many times in many interview you will be asked about this. Yeah. In fact, this Maxwell's equations, how it comes and all these things, the line by line derivation of all these things, you will study it later on when you study microwave engineering. That time you will be studying all these things. Okay. Right now, okay, I'm just showing you the equations. Okay, these are the 4 Maxwell's equations, and these I'm writing it for the free space. Okay, I'm writing it for free space. Now Gauss law, you know, this is the Gauss law actually. Gauss law is this. Okay, the Gauss law is given by this. Now for a charge-free space, if there is no charge in the space, see, when I'm transmitting the signal in the space, there is no charge. The charge is space is this our wireless medium is not charged. Okay, so in a free charge-free space, this rho is the charge density. This rho is equal to 0, and hence this divergence of E will be equal to 0. Divergence of B is equal to 0. Again, the derivation you will get it, you will study it afterwards. For the time being, you just take it for granted that this is the second equation of Maxwell. Divergence of B is equal to 0. Okay. Then curl of E is given by this. This actually corresponds to the Faraday's law of electromagnetic induction. Okay, the rate of change in the magnetic flux that produces the voltage and all these things, you know that. Okay, so this is actually the relation, that is the relation given by this. Okay, this is the Faraday's law of electromagnetic induction. Then Ampere's law, you know. Okay, so the Ampere's law is actually curl of B is equal to mu J. Okay, this is the Ampere's law, that magnetic field is produced when current flows through a conducting wire. J is the current density. J is the current density, current by area, on area of the conductor, cross-sectional area of the conductor. So Ampere actually said that curl of B will be equal to mu J. Maxwell, however, he modified it and he added this term. This is actually you might have studied. I don't know whether you have studied. This is due to the displacement current. This is due to the displacement current. Okay. So this is the modification that was made by Maxwell. And now if there is no conducting current, okay, so J is equal to 0, okay, there is no conductor, no conducting current flowing through your wireless free space, okay. In that case, curl of B will come out to be equal to mu into epsilon into del E del T, okay. And for free space, we are writing mu as mu naught, epsilon as epsilon naught, okay. So these are the 4 Maxwell's equations, okay. So you just, for the time being, you just remember it. So you need not to know the derivation and all these things. You just remember it. Later on, you will study it in details. So based on these 4 equations, we are getting the wave equation. How? First, you take the curl on both sides of this equation, the third equation. You take curl on both sides, and I have shown here line by line. Anyway, you need not to remember line by line. You can just say that based on this third equation, taking curl on both sides of the third equation, you get this. You will get this. Okay. Similarly, if you take curl on both sides of the fourth equation, you will get this. So these two are basically the wave equations. Now, what is this mu naught epsilon naught, this product? What is it? Let us see. Mu naught, this epsilon naught, you know, it is the permittivity of the free space, and it is the value is given by this. Okay, this is the value given by this farad per meter. Okay, permeability of the free space is given by this Weber per ampere meter. Okay, or it is Henry per meter. Okay, so this is the permeability epsilon naught mu naught. So if you multiply this 2, you get that this will be equal to mu naught into epsilon naught will be equal to 1 by c square, where c is equal to 3 into 10 to the power 8 meter per second velocity of light. You can just check it. Okay, it will come out to be like this. Mu naught epsilon naught will be equal to 1 by c square. So I can write these 2 equations, the 2 equations that I am getting here. I can write it as this. So this will be the EM wave equations. I can write EM wave equations like this. And you know what is this delta square? This delta square is del square del x square, del square del y square, del square del z square. Okay. So you see how this one, whereas here I have shown here for this wave, you see that here I am doing del square del x square. It is only for x in one direction only, whereas here I am taking it, this del square is more generalized. It is del square del x square, del square del y square, del square del z square. Okay, so you can just compare this, that this is actually the general equation for wave equations. Okay, and since as we are considering that epsilon is this E and B, they are along the y-axis and z-axis. Okay, I can accordingly, just following what we are not going into details, but following the general wave equation, I can say that the solution for those 2 equations I will be getting like this. Okay, actually, if you do solution mathematically, if you do solution for this, if you use that partial derivative and the PD solution by all these things, if you do this, you will get the expression in terms of some exponential e to the power j theta. You know, j is the imaginary, okay, root over minus 1. So it will come in that form, e to the power j theta. And you know, e to the power j theta is basically cos theta plus j sin theta. So you have a real part and imaginary part. So if we take only the real part of that solution, okay, so if we follow the actual mathematical solution for a partial differential equation, it will be of the form of e to the power something. And then if we take that real part of it, then it becomes only the cos part. Okay, and that gives you these two relations, this ext. And anyway, we are not going into details. I'm just relating this, that the same equation you get it in the general wave equation. So accordingly, I'm just putting it directly, that ext will be equal to e naught ka cos kx minus omega t plus phi. Similarly, bxt, you will be getting the wave equations in this. Okay, so these are the two wave equations which I have already shown you in a picture also. These are the two wave equations. Okay, so this is how from Maxwell's equation, four equations, if you solve them, you get these two wave equations. This is how they are obtained. Okay, so this is what actually these physics people they were doing that time. Actually, Maxwell did all this calculations, all these things, but everything was mathematical till that time. Okay, he did all these things, but it was mathematical. Only Hertz, he found out that there is some electromagnetic wave. Okay, but he was not able to generate that electromagnetic wave and transmit it. He observed the existence of it, but he was not able to generate and transmit it. Tesla was the first person who actually transmitted to some extent, but that also not too far. And then, as I said, the first time it was the actual transmission system and all these things were made by J.C. Bose, so that this electromagnetic wave could be transmitted to a longer distance. And then Faraday took over that work. He studied that work and he commercialized it, and he made a commercial radio system. Okay, that is how actually the first ever electromagnetic this radio system came into existence. It was just the last point, that this when we are having this E and H, this two waves, the electric field wave and the magnetic field wave, these two waves, as I said, that the direction of propagation of the wave is along the x direction, which is perpendicular to both E and B. Okay, and that direction, the direction of that propagation of the electromagnetic wave is given by the cross product. You know that cross product will always give you the direction in the perpendicular direction, E cross H. Okay, and this E cross H, this direction, direction of propagation of the power, electromagnetic power. Okay, this is called Poynting vector. This vector along E cross H, this vector is called Poynting vector. This Poynting is the name of the person who actually said that. Okay, he actually said that E cross H is the direction, and by this only we can find out the magnitude of the power transmitted as well as the direction of the power transmitted. So this is how the direction of the power flow due to electromagnetic waves can be calculated using the Poynting vector. Okay, so till today it is I think that's enough. Just I have given you some basic idea about the electromagnetic waves. Okay, so we'll continue in the next class. We'll talk some more about this EM wave. Okay. Okay, any question? Who are not having any question, then I think you can now leave, because your time is over now.
Thank you, sir.
Thank you, sir.
Thank you.
Okay.